tin wires before putting them in motor controllers or servo controllers. This helps keep it organized and make sure you have a reliable connection. That way the wires don't spread apart and come out of contact. Also using a power bus for electronics. This is an example of the Anderson power bus. This allows you to provide redundant power supply to all your motor controllers. So instead of, say you lose, if you're doing daisy chain electronics with the power, and you lose power farther up the chain, then all the controllers afterwards also go out. Just like the old style Christmas tree lights where one of the lights went out, then all the rest down the line would go out. Charge batteries, you want to make sure that you're charging batteries between matches so that you have fresh ones for every match. You also want to do this at practice, only run a couple rounds with autonomous and teleop because you still want to make sure you're running at a pretty reliable rate because it can affect distances you travel and stuff like that. And then power supply and DC motor power consumption. So, let's see you guys numbers. Motor controllers supply up to 4 amps per channel, and motors running at max efficiency are at 1.05 and 2.46 amps is the max output. So you don't want to have any more than 2 motor controllers on a single board, or else you won't be able to get that maximum output, or get even close to maximum. Okay, Tamiya versus PowerPole. The Tamiya is the one on the right or the left? Yes. Right. Anyway, that's the one that comes standard on the batteries and the chargers. It's not a very good connector, and it's not rated for nearly as many cycles as an Anderson PowerPole. After a while, that one's going to wear out, and it's going to start to give you an unreliable connection. So we recommend switching over all your batteries and chargers to the Anderson PowerPole. They're rated for a lot more cycles, and you can't plug them in. How it works is it's like a tongue, and they tuck in. It's just a lot better connection.
What's a cycle?
Plug it in and unplug it. Oh, mine again. I2C communications. So shorten your I2C wires, and you want the total length to be less than 3 feet. So coming from the NXT to the end of that motor controller or servo motor controller chain, you want that total distance to be less than 3 feet. The I2C protocol voltage, Mr. Diamond knows better, but how it works is, so you're getting 12 volts initially, and then at the first controller, you're getting 6, and then it halves again, 3, and then 1.5, so it keeps happening. And what does that affect? How does that affect it?
So a couple of things there. So the halving is how they figure out the daisy chain. So if you convert a digital signal to analog, greater than a certain voltage is a 1, less than a certain voltage is a 0. So if it's a 1 or a 0 for the first controller, you're passing above 6 or below 6. Maybe it's, something like that. Maybe it's half a 6 even at that level. Then all the no's get passed down to the next controller to see if he wants to deal with them, except his total range is only half the range of the first controller. He's now dealing with 3 volts to 0 volts. And anything below 1.5, he says it's a no, but I'll hand it down to the next controller in case he needs it. He's now looking at a range of 0 to 1.5, where 0.75 and above is a 1, and below 3/4 of a volt is a 0. And so as this chunk flows downstream, and it's done with a series of resistors in here that keep having the current, your signal's pretty fragile by the end. 30 feet is very optimistic. We were having troubles at 30 inches. We discovered by happenstance that if you look at our last 2 years' robots, our electronics are all together with very, very short cable runs. All together with very, very short cable runs. Scattered all over the robot with long cable runs, and we had more I2C failures than we had ever before had. And it wasn't until late in the season that we understood the problem, and by then it was too hard to do much but shorten them up some. And one of the things we did is we put, since we were already using 2 channels for controllers, we put 3 on one channel and 2 on the other, where we had been 4 and 1, shortening up our longer cable run. Talking to Tim at Robot C, I can't remember his last name now. He's who put us on to this, and definitely do everything you can to keep the I2C ID or NXT cables as short as you possibly can. And a comment he shared with me, one of the problems they're having with the EV3 right now, they can't get past 2 motor controllers reliably. By the time they try to propagate the signal to a 3rd controller, it's having issues. So it's this same problem, only worse right now.
Interference with motors. Yeah, interference with motors. Running wires, information cables past motors can cause problems with electric fields that the motors create while they're spinning. And then wire chokes can help eliminate some of those problems. They act as sort of antenna for high frequency. The wire choke makes it so that your wires don't act as antennas for radio frequency. Right.
Okay.
Good talk, Brian.
Okay, cool. So this is more for the first year teams that we have. And this is basically a, what we call a bench model of everything that you could possibly have on your robot in your first year. It's pretty basic. So we have 2 servos and 2 different types of drivetrain that you can have. This is a sprocket and chain connected to motor, and this is just to connect a direct connection to the motor. And then this is your on switch, and as I said, the power distribution center. And then, of course, your SMIC module.
Although the grounding to the field itself is illegal this year, as we said earlier, that doesn't mean that you can't ground things to the frame of your robot. So in other words, what I'm saying is you want to try to equalize the charge across your robot to a single charge. So connect things to your frame. This can be done with wires, this can be done with, we have a special type of copper tape that has a conductive adhesive that's really good for connecting things like plastic. And you especially want to do your plastic. This was a mistake we made early on in our FGC career that, we first thought the plastic acted as an insulator, which is true in ways. But we thought, well, static electricity can't affect an insulator, right? I mean, it can't conduct any electricity. Well, we were kind of exactly wrong. Instead, plastic acts as a capacitor. So this means it builds up charge and it holds a charge in the plastic until it finds a way to release it. In other words, an electrostatic discharge event. So this is when all of the plastic has this built up charge and it's just holding it and waiting for something to touch it, and once it does, it releases it all in whatever it touches, which is that static shock you get, like after you slide down the slide and touch something metal. So plastic acts as a capacitor, so make sure you ground your plastic to the frame, connect it with something like copper tape. You can see actually on that robot right there, there's copper tape running across the shields to equalize the charges. And also ground your electronics. So we run a piece of copper tape over the electronics, and we either have a board that is the board that the electronics sit on that is dissipative or conductive, or we run copper tape to the frame from there. So once again, you're not allowed to intentionally ground in the field, but you can definitely equalize charges across your robot. The other thing we have is we have a static detector. So this is a little thing we built. We found the design for it online, and we have a couple here that we might be able to demo if you really want to see one. And basically what it does is if it detects a positive charge or a negative charge based on how it's set up, the light will turn on. If it detects the opposite, the light will turn off. And what you're able to do is just take your robot, run it for a little bit, and then take a static detector and just move it around your robot. And if you see the light changing as you move it around, it means that there's a difference in charge across your robot. There's a potential for an ESD, an electrostatic discharge event.
Cougar Robotics, this is the device we made to detect differences in charges across the robot. The green LED will change as the charge of the area changes. On this one, a negative charge is green and a positive charge is off. Here we have two sheets of plastic, one that has copper tape on it, the top one, and one that does not, the bottom one. After running the robot in game conditions, we took the detector to look for a difference in charge. The top shield, which had copper tape on, had a constant charge throughout. On the other hand, the bottom shield with no copper tape on it had a difference in charge in the middle versus the edges. Static electricity is typically very high voltage with very low amperage. Differential static electric charges create a potential for ESD events, or electrostatic discharge events. ESD events can cause electronics to reset or lock up. After taking these precautionary measures, we have noticed a significant drop in disconnects from the field, as well as brick freezes.
Another really good practice is using a semantic bracket of some sort. So you can actually see there are two different ones pictured here. The one on the left is one designed by Andy Mark that is 3D printed, and then the one on the right is one that we designed. And we actually have a bunch of those here if you need one, and we'll give one to you. Basically what it does is it makes it a lot easier to mount the semantic bracket, gives you a lot more holes to mount it with, but more importantly, as you can see the bottom there, it holds the cable into the semantic. So instead of plugging the cable to flash your semantic directly into the Semanto, we have little USB extension wires. So instead of putting a lot of cycles on the USB on the semantic module, we use the little tiny USB cable and we put all of the cycles on the little tiny USB cable. And so if that ever starts to wear out, we just replace the USB cable and the semantic's still good. Along with that, since they're zip tied down, even in game conditions where you're getting bounced around, you're getting hit, you don't have to worry about the cables coming out of your semantic. So once again, if you guys need one or you want one, we have a bunch with us.
You can download the specs for the Andy Mark one for free off their site. So use it in 3D printer.
Okay, so as we were talking about, static is a big issue, and one of the things that we do to prevent static is have metal panels on our robot, as you can see in the pictures above. We originally, as you can see on the left, had plastic panels, and now the same thing that Cougar did, that we just got a ton of static shocks, and then on the picture on the right, we went to a metal panel, so we didn't have those as much. And another thing that we do is before each match, we spray a microfiber cloth with some static spray and rub all of our panels and plastic down before each match just to make sure that we get every static gone.
Here's a really simple way that we like to test all of our electronics. So this piece of corrugate right here was a game field element a while back, but what we basically do is we just drive the robot over it and try to get it to bounce as much as we can. Ignore the wire out the back, that's on purpose. But what you're trying to look for is the robot to ever drop connection. If you see the power on the Samantha flash, if you see something stop working, you know you have a loose connection somewhere. Just a really simple way to do that. And one thing that I think Mr. Diamond said earlier, but we really want to emphasize, is try to own all of your disconnects. We've seen some teams that will say, oh, it was the field, or oh, it was the FCS system. It's one of the things that we did when we started out too, but I think it was either the bold over year after, we just started to own all of our disconnects. We tried to find reasons that it could be us. Tried to find ways that we could fix the problem. Even if we were 99% sure it was the field, we'd still try to find a reason it could have been us. So own all of your disconnects, and you normally have a lot less of them.